So consider an ellipse and a fixed point M. In this case, M is on the boundary, and another point P of t that I can move around on the boundary of this ellipse. Now for every P of t, I'm going to draw the tangent line at P of t, perpendicular to the normal, and I'm going to drop a perpendicular from M, wherever M is, to that tangent line, and I'm going to locate this foot of the perpendicular here. Now the locus of this foot over all positions of P of t sweeps out what's known as the pedal curve of the ellipse with respect to point M. Okay, now on this video, I'm interested not only in observing the geometry of these curves as I vary M, but I'm also interested in figuring out what's happening to the area of this curve. So if I click here, I'm numerically reporting the area of this curve and also the perimeter of this curve, which I'm less interested in. You can see here that, of course, for any P of t, that foot of the perpendicular is going to be always on the curve, right? Now, as I vary, for example, M along this ellipse, what's going to happen to the perimeter and the area of this curve? Let's do that. You can see that they're both varying. Okay, so there's no invariance there. I'm looking for invariances. Okay, now let's go ahead and show you guys the result. If I go, for example, to a circle, okay, now M is located in this green circle, concentric with the ellipse. And I vary, so now you're seeing here this strange evolute, right? It has a different kind of a shape to it. I'm going to vary M now with respect to that circle. M is going to be sliding on that circle, and I can track what's happening to the area of this evolute. You can see it's not changing, at least numerically. So the first result that I want to share with you guys here is that the area of the evolute is invariant over M. Now, this evolute is not always a non-intersecting curve. Let's force this ellipse to have a higher kind of a, I believe the evolute can be, oh yes. So if I place M outside of the ellipse by increasing the radius of this green circle, okay, now as I approach the vertex, this curve can assume self-intersecting configuration over a range of M's, right? So let's make this circle even bigger so we can exaggerate that a bit. And I'm going to animate M, and we're going to follow this numeric calculation here, which is the signed area because it's self-intersecting. So I have to have a standard to compute this area. I'm computing so-called signed. It has a sign, plus or minus area. So after the first cross intersection, you're counting this inner area. Here's a negative value. But even then, as M moves on this green circle that is concentric with the ellipse, and this shaking around here is just an artifact of Mathematica. I think if I change this to 4 into 4, the shaking might go away, maybe not. All right. But the first cool result here is that the area of these evolutes is constant as long as M is moving along a circle. Of course, the area changes for every circle. We don't have an expression for that yet. We hope to get that soon. This is a pretty cool result. Okay, the second kind of curve that I want to talk about here is the contrapedal curve. What's the contrapedal curve? So let's get rid of the curve. Let's get rid of the stats. And I'm going to show you guys another construction. Now the contrapedal curve, let's place M back on the ellipse so we can see this again. M in general can be anywhere on the plane, right? The contrapedal curve is the locus of feet of perpendicular, not dropped from the tangent passing through P of t, but dropped from M onto the extension of the normal at P of t. So as I vary P of t, and I just continue that line that starts at P of t and is oriented or directed along the normal, if I drop a perpendicular from M onto this line, I get a point, and the locus of this point is known as the contrapedal curve. Let's draw it. Here's the contrapedal curve. It's a different beast. Okay, so here's a contrapedal. Let's go back to the pedal or the pedal. You can see that they're different beasts. Okay, so let's talk about the contrapedal right now. So first of all, let's observe this phenomenon as I animate P of t so we understand better what's going on here. Again, I'm dropping perpendiculars from M onto the line that passes through P of t and is directed along the normal. Okay, and the locus of those feet of perpendiculars. Here's a foot, right? The locus of this foot of perpendiculars over all P of t gives me this contra-pedal curve. Now, this curve also has some really interesting geometry. Okay, it can be multiply self-intersecting, can have this sort of ribbon over here, or let me look for a better word. But you can see here that it can self-cross, and it has quite interesting geometry. Okay, I think it's regular. It never has a sort of a sharp cusp. Curve is always smooth, right? That's pretty cool. Now let's look at the area. Let's calculate the area. L is the perimeter and A is the area as M is animated over the boundary. Okay. Now again, the area is changing, and the perimeter, of course, is changing as well. Now let's animate M now using the same kind of technique over a circle. So I've placed a circle in here. You can see here that as I animate M, you get the same phenomenon. The area is just totally invariant. Let's change the radius of M. Sorry, let's change the radius of the circle M is riding on. Let's make it go outside of the ellipse. And let's see what's going on. Numerically, the area is just invariant. Let's observe this geometry. So invariance of contrapedal curve area for all M on a circle concentric with the ellipse, and the same result. Let's switch back to the pedal curve. The same result of area invariance. Let's reduce the radius of the circle. You get area invariance for the pedal and for the contrapedal curve. So this is today's result, guys. I hope you've enjoyed it.